Hey guys, we are back with another interview problem, that is minimizing taxis for maximum efficiency. Okay, so first we'll understand the problem, then we'll discuss the approach to solve the problem, and then at the end we'll write the code. So this problem is also known as share taxi scheduling problem. Okay, so imagine you manage a share taxi company. You have a wealth of historical trip data, including the trip IDs, the start time, and the end time. Your goal is to determine the minimum number of taxis required to service all these trips without any taxi being double booked. Okay, so no overlaps. Additionally, you want to assign each trip to a specific taxi for a optimal scheduling. So let's take few examples. So here in example one, we have a trip A. A is the trip ID and the start time and the end time. Similarly for the B, start time, end time, and likewise we have 5 trips. And we have to find the minimum number of taxis required. So here the answer is 3. Why 3? That we'll see in a moment. And also for each taxi, you need to print the trips assigned to that particular taxi. Okay, so let's understand this. So here, let's draw this. So the maximum time is 10. So start with 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so A start time 1, end time 5. So this is A. And B start time 2, end time is 10. So this is B. C start time is 5 and end time is 7. So this is C. D start time is 6. So this and end time is 8. And E start time is 7 and end time is 9. So E is this is E. So here we can see that A and B, these two trips overlap. So these two trips cannot be assigned to one taxi. So let's say we have taxi 1 and we assign A to it, and taxi 2 will assign B. Now trip C, C starts at 5 and whereas ends at 5. So definitely taxi 1 can take trip C. So we'll do C here. Now the C and D overlaps, right? So D cannot be assigned to taxi 1, and D and B also overlap, so it cannot be assigned to taxi 2 as well. So we'll have another taxi and we'll assign D to it. And now D is done. And E, so D and E overlap, so it cannot be assigned to 3. And D and E and C doesn't overlap. So B ends at 7, sorry, C ends at 7 and E starts at 7. Okay, so we can assign E to the first taxi. And now we are done. So we need 3 taxis which can cover all these trips. Okay, so that's why we need 3 taxis, and these are the assignments. Now let's take a few more examples. So here in this example 2, we have a start time 1 and time 4 for trip A. So A, D, E. So A, D, 1 to 4, 5 to 6, and 6 to 8. So assigned to taxi 1, and 2 to 3 and 3 to 5 assigned to taxi 2. So minimum number of taxis required is 2. Okay, and let's take another example. So here 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. So you need only one taxi to cover all of these trips. Okay, now let's see how we can solve it. So here we are going to use the greedy algorithm. So here we have trip A 1 to 5, 2 to 6, 6 to 8, 7 to 9, and C is 5 to 7. So first thing first, we need to bring these trips in some order. Since we have to cover all the trips, we cannot escape any of the trip. Okay. So first thing what we will do is we'll sort these trip by their start time. Okay. So we'll sort the trip by the start time. So this is 1 to 5. B is 2 to 6. So 1, 2, 1, 2, and then next smallest is 5. So C 5, 7, D is 6, 8, and E is 7, 9. So now we have sorted these trips in ascending order as per their start time. Okay. So next we are going to iterate these trips. So first take the trip A. So we have selected the trip A. At present, we have no taxis. So we'll take the taxi 1, let's call it as T1, and then assign A to it. And we'll store the end time. Okay, so the end time is 5. So the end time is 5. So next we'll take trip B and we are going to compare the start time of B with the end time of A. Okay, so the end time is 5 and the start time is 2. That means that trip B starts before the trip A ends. That means we cannot assign this trip to this taxi T1. So we need another taxi. So let's create another taxi T2 and assign B to it. Now the next trip is C and the C start time is 5, right? Now the problem is we have two taxis and we'll have to check if this trip C can be assigned to taxi T1 or T2. So we have to compare the start time of C with the end time of taxi T1 and taxi T2. And if for any of the taxi, if the end time is less than the start time of C, that means that taxi can take this trip C. So we'll have to iterate these both the taxis, compare the end time with this start time, right? So trip A end time is 5, and trip B end time is 6. Now the start time for trip C is 5. So T2 cannot take this because the end time for T2 is 6 and the start time for trip C is 5. But taxi T1 can take this because end time is 5 and the start time is 5. So we'll assign this trip to taxi T1 and update the end time to 7. Okay. Now the next trip, which is D. So the start time is 6 and end time is 8. So again, we are going to compare the start time of trip D with the end times of both the taxis. So start time is 6 and here for taxi T1 the end time is 7. So T1 cannot take this trip. But T2 the end time is 6 and for T the start time is 6. So T2 can take this. So taxi T2 will take this trip D and we'll update the end time to 8, which is the end time of D. Now we are done with D. So the last trip is E. The start time is 7 and we are going to compare this start time with end time of both the taxis. So T2 end time is 8 and this start time is 7. So E cannot go to T2, but for T1 the end time is 7 and for E the start time is 7. So it is assigned to taxi T1. So this is E and we'll update the end time to 9. So we need two taxis to cover all these 5 trips. So let's see the time complexity. So we are doing the sorting. So O of n log n here and here, O of n for the iteration and O of n for comparing it with the number of taxis. In worst case, all the trips would be overlapping and number of taxis required would be equal to number of trips. So in worst case, here the time complexity would be O of n and for iteration O of n, so overall time complexity would be O of n square. Now, can we reduce this time complexity? And the answer is yes. Now let's see how we can reduce it. So here we are iterating the number of trips that we cannot reduce. We need to go through all the trips. But here to check which trip will be assigned to which taxi, we are iterating through all the taxis. And this is O of n. This is definitely we can reduce. So for that, what we can use Min-Heap. So basically, all these taxis will be in the Min-Heap, and this Min-Heap will be created as per the end time of the taxi. Okay. So at any given point of time, the top element in the Min-Heap That means the top taxi at the main heap will have the smallest end time. So when we check if trip can be assigned to any of the existing taxis, we don't need to go through all the taxis end time. What we'll do, we'll look at the top element in the main heap. Basically, the top taxi in the main heap will have the smallest end time. And when you're checking for a trip, if that can be assigned to any of the taxis, you'll just compare it with the top one. So if you cannot assign the trip to this taxi, that means you won't be able to assign it to any other existing taxis because the top taxi in the main heap has the smallest end time, right? So what you will do in that case, you will create another taxi, assign that trip, let's say F, put the end time, and insert it in the main heap, right? So we know the insert operation for the main heap is log n, right? So this way we can reduce the overall time complexity O of n log n from O of n square. So far we have understood the problem. We have discussed the approach as well. Next, we are going to write the code for this. So let's start with the Java code. So here I have created a simple class share taxi problem. So first we are going to create a class for trip. So let's call it as class trip. And this has the trip ID. So let's call it as name and in start time and end time. Now let's create a constructor for this. So we have our trip class ready. So let's create a driver method. And here we'll have these many trips. And now let's create a function to solve this. So let's say find is the function name. And this take trips as an input. So first we are going to sort these trips as per their start time. So let's say array start sort. Okay. Next, we are going to need a min heap to store the taxis. So before that, let's create a class for taxi. So static class taxi. And what do we need in taxi? The taxi ID. So int ID and the end time for the taxi. So end time and list of all the trips this taxi can take. So list. Now let's have a constructor for this as well. So constructor and all we need is ID. And when we are creating a new taxi, we need to initialize this list. So new array list. Now let's override the toString method as well so that we can print these taxis at the end. So toString and ID and time in the trip names. Okay. So now we have the class for taxi. Now we'll have a min heap for this taxi. So taxi and let's call it as heap and new priority queue and we'll override as per the end time of the taxi. So okay, so now we have the heap as well. So next we are going to iterate the all of the trips. So for trip in trips. So first we'll check if heap is empty. If yes, that means there are no taxis, so we need to create a new taxi. So let's do one thing. Let's have another function here and call it as a return type is taxi and this function will be get new taxi. Okay, and what we'll pass the trip to this. So we'll create a new taxi So taxi, new taxi. So this constructor takes ID. So yes, every time you create a new taxi, you need a new ID for that taxi. So let's have a global variable here. Let's call it as static int taxi ID. And let's start with 0. And every time we create a new taxi, we'll assign this ID and increment this taxi ID. So we'll do taxi ID plus plus, and the end time for this taxi would be the end time of the trip. So trip end time, and we'll assign this trip name to this taxi. So taxi dot trip names dot add trip dot name. Okay, and return the taxi. So here, if the heap is empty, we'll create a new taxi and add it to the heap. So heap dot offer get new taxi. Okay, so this will be static as well, and we'll pass the trip. Okay, else. So now if heap is not empty, that means there exist few taxis, and for the current trip, we need to find if that trip can be assigned to any of the existing taxis. If not, we'll create a new one. Now we don't need to go through all the existing taxis as we have discussed here. We don't need to go through all the taxis. We need to compare it only with the top taxi in the min heap. So what we'll do, if heap dot peak dot end time, if this end time is less than equal to trip start time, that means this taxi which is at the top of the heap can take this trip. So what we'll do, first we'll remove the taxi from the heap. So heap dot remove, and then we will assign this trip to this taxi. So taxi dot end time, we'll update the end time to the trip end time, right? Then we'll add the trip name to the taxi. So taxi dot trip names dot add, and then again we'll put this taxi into the heap, right? So again, if taxi at the top of the heap can take this trip, we'll take the taxi, update the end time, add the trip to the taxi, and put that taxi back in the heap. And let's say if that condition is not true, that means none of the taxis in the heap can take this trip. So we need to create a new one. So basically, we need to create a new taxi, right? So once we are done with the iteration, we'll have the heap, which have the taxis and the assigned trips. So what we'll do, we'll print all the taxis. So while heap dot is empty is false, what we'll do, we will print heap dot remove. Okay, so let's call this find method from our driver function. So here, and we'll pass the trips. Now let's run this. Okay, so we have the output. 3 taxis are required, 0, 1, and 2. We have end time for these taxis. That's good. And we have the trip names as well. ACE to taxi 0, BF to taxi 1, DG to taxi 2. So we need 3 taxis to cover all of these trips. So now let's go back to the problem. Let's quickly read this approach. It's a greedy algorithm. Sort the array of trips based on their start time. Use a min heap to keep track of the end times of the trip, always allowing access to the trip that finishes the earliest. Okay. Now iterate the list, iterate the trip. For each trip, if the heap is empty, new taxi is created and trip is assigned to it. If taxi at the head of the heap can take this trip, that is end time is less than equal to the start time of the trip is assigned to this taxi and the taxi end time is updated. If taxi cannot take the trip, a new taxi is created and the trip is assigned to it. After processing all the trips, the heap will have all the taxis and their assigned trips. This is how we can solve this problem. Now we can mark this problem as completed, and we'll see you guys in the next video with another interview problem. Till then, bye bye.